Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.
To our honorable speaker, Chemist Tasnim, Muhammad Yusof, and Professor Gunawan, to Professor Darmawan as a head of chemistry department of Diponegoro University, and Buyayu as the person in charge for this joint webinar series on chemistry, all our colleagues from University Sains Malaysia, and Dr. Tanwini from University Sains Malaysia, and all the participants of this joint webinar. So welcome once again to the 5th joint webinar series on chemistry. Today we will have our first speaker, chemist Tasnim Muhammad Yusof, with the title ENR 50-based polymer electrolytes for electrochemical device application, and Professor Gunawan with the title of Photocathode of copper indium sulfide preparation by electrodeposition and sulfurization for hydrogen generation by photoelectrochemical water splitting. Before we start our joint webinar chemistry, I would like to invite Dr. Tanwini for giving opening remark for this joint seminar. So for Dr. Tanwini, the layer is yours.
Okay, thank you, Dr. Basit. Good afternoon all and selamat petang dari Malaysia. Okay, so first of all, on behalf of the Chemical Sciences Program, School of Distance Education, University Sains Malaysia, I would like to thank the Chemistry Department, Faculty of Science and Mathematics, Universitas Diponegoro Undip for organizing this joint webinar series on chemistry. So today marks the 5th webinar between USM and also Undip. So I believe that this activity will surely benefit both institutions and also foster our collaborations in many areas. So thank you all for being here today. Dr. Basit, now I pass it back to you. Thank you.
Thank you, Dr. Tan, for the opening speech. Now we have come to our speaker. Before we start with our speakers, I would like to share the CV of our speaker this afternoon. The first, I would like to share, anyone could see on your screen? Yeah, this is the curriculum vitae of our first speaker, chemist Tasnim binti Muhammad Yusof, MSc. She is a lecturer from Chemical Sciences Program, School of Distance Education, University Sains Malaysia. Her email address is anistasnim@usm.my. Her research interests about polymer electrolyte, polymer blend, and regard with rubber, nanomaterials. Her educational background, he obtained her MSc in chemistry on August 2007 from School of Chemical Sciences, University Sains Malaysia, while previously her BSc was obtained on June 2004 from the same university, University Sains Malaysia. She has a long professional experience, start from June 2006 until September 2009 as a researcher at Sirim Berhad, and start from October 2009, she became a lecturer in Chemical Sciences Program, School of Distance Education, University Sains Malaysia. There are some publications of our first speaker about the conductivity of diethylene glycol dibutyl ether or epoxides, natural rubber based on composite polymer, etc. And I would also like to share the curriculum vitae of our second speaker, Professor Gunawan. Professor Gunawan is a full professor at the Department of Chemistry, Faculty of Science and Mathematics, Universitas Diponegoro. With his email is gunawan@live.undip.ac.id, or you can also send the email to his second email, gunawan@lecturer.undip.ac.id. His research interest about PEC water splitting, thin film solar cell, plasma technology, and he has a huge publication with total number citation above 1,400, and each index with in Scopus about 11, and total publication in Scopus up to 63. His educational background, he obtained his BSc in Department of Chemistry, Kacamata University Indonesia, MSc in Department of Chemistry, Kacamata University Indonesia, while his PhD was obtained in 2015 from Osaka University, Japan. And these are some of his publication. If you want to know more for the publication of our booth speaker today, you can just check their publication in Scopus or in Google Scholar. So for now, we will have our speaking session for each speaker. We give you around 25 minutes. So the first from each of speaker will speak about 25 minutes. So Chemist Anis will talk about 25 minutes, and then followed by Prof. Gunawan for 25 minutes. And then we will have the third session as the discussion session. Anyone can raise your hand to ask question or anything to both presenters for around 10 to 15 minutes. So let's start from our first speaker. For Chemist Anis Tasnim Muhammad Yusof, the time is yours.
Okay, first of all, I would like to thank Dr. Nobasit for the kind introduction, and it's an honor to be here with all of you today. Okay, and my presentation title today is NR50-based polymer electrolytes for electrochemical device applications. Okay, first of all, what is polymer electrolytes? Polymer electrolytes are ion-conducting materials in which ions move through a polymer matrix. Okay, it will enabling ionic conductivity without the use of traditional liquid electrolytes. And they are typically composed of a polymer host, okay, such as polyethylene oxide, okay, which provide a flexible and solid or gel-like medium, okay, along with the dissolved salt that supplies mobile ion, okay. The dissolved salt like lithium, okay, or sodium ions, okay. And the polymer matrix enables the ions to move via segmental motions on the polymer chains, okay, which creates transient paths that ions can follow. Okay. And this movement of ions within the polymer matrix generates ionic conductivity, and it will allow for charge transfer across an electrochemical cell. Okay, this is the principle of ionic conductivity in polymer electrolyte, which is we have salt dissociation. Okay, in salt dissociation, the polymer matrix help dissolve and dissociate the salt, okay, and then creating free ions, okay, and this one will contribute to conductivity. Okay, and common salt used in polymer electrolytes is like lithium chlorate, okay, LiTFSI, okay, all of these will always use in the polymer electrolyte, okay, and all of these will release mobile ions, okay, into the polymer matrix. For the polymer segmental motion, okay, in polymer electrolytes, ion transport is facilitated by the segmental motion of the polymer chains, okay, especially in the amorphous, okay, which is non-crystalline regions where the chains have the greater flexibility. So the segmental motion creates the free volume or spaces, okay, in the polymer through which ion can pop, okay, and it will allow for the ion transport. Okay, another one is the glass transition temperature. Okay, all of us know that the glass transition temperature of the polymer will affect its flexibility. Okay, and the polymers above their TGs are more flexible and allow greater segmentation motion, and it will result in the higher ionic conductivity. And polymer with low TG values, okay, or plasticizer that lower TGs, it increase the chain mobility and will improve the ion transport. Another one is the ion polymer interaction. Okay, ionic conductivity in polymer actually depends on the coordination between ions and the polymer's functional group. Okay, and this interaction stabilize, okay, ions within the polymer, but must be balanced to allow free ion movement without too strong a bond to the polymer, okay, which it will reduce the mobility. Okay, this is the type of polymer electrolytes. Okay, we have solid polymer electrolytes, composite polymer electrolytes, plasticized polymer electrolytes, and also gel polymer electrolytes. Okay, for solid polymer electrolytes, okay, it is formed by incorporating inorganic salts into the polar polymer, okay, and then the electrostatic interaction between the metal ions of salt and polar polymer will result the formation of the coordination bond. And this metal polymer interaction can be affected by a factors such as nature, okay, and distance between the functional group of polymer, molecular weight, okay, nature of branching, okay, all of this in polymer, okay. And when the polymer electrolyte is placed in the electric field, the ion start to move from one coordination site to other, okay, and it occurs due to weaker interaction between the metal ion and functional group of polymer chain. And for solid polymer electrolytes, we have high flexibility, okay, we have thermomechanical and chemical stability, and also low ionic conductivity. Okay, and for the second types of polymer electrolytes, we have composite polymer electrolytes. Okay. Okay, composite polymer electrolytes. Okay, in the composite polymer electrolyte, conductivity of polymer, okay, also decrease due to presence of ion pair formation. Okay, this behavior is observed mainly because of the low dielectric constant of polymer matrix. Okay, to overcome this issue, okay, high dielectric constant in organic fillers such as TiO2, SiO2, okay, are dispersed into the polymer electrolyte to avoid ion-ion dissociation. Okay, the obtained electrolyte combines the properties of ceramic filler as well as polymer and will result the flexible, mechanically stable composite polymer electrolyte. Okay, how about plasticized polymer electrolyte? In plasticized polymer electrolyte, we have high conductivity and low mechanical and chemical stability. Okay. Plasticized polymer electrolyte are formed by dissolving low molecular weight compound, okay, of ethylene carbonate, okay, propylene carbonate, okay, polyethylene glycol, okay. All of these we call it plasticizer, okay. And this plasticizer, okay, reduce the inter and intramolecular interaction between the polymer change and reduce the TG and crystallinity of polymer chain and enhance the salt dissociation ability. Okay, and the last one is gel polymer electrolytes. Okay, okay, and all the polymer-based electrolyte, okay, gel polymer electrolytes, or we call it JPE, okay, our focus must attention because they combine the advantage of liquid electrolyte, okay, such as high conductivity, okay, good electrolyte contact, and solid electrolyte, okay, okay. And in GPEs or gel polymer electrolyte, okay, polymer is used to trap the liquid constituent and provides mechanical support, and it is considered as safer than liquid electrolyte. Okay. And for the synthesis of gel polymer electrolyte, large amount of organic solvent is used in the polymer in which its conduction take place along the host polymer. Okay, this is the advantages of polymer electrolytes. Okay, polymer electrolytes actually offers several advantage over traditional liquid electrolytes. There are several advantages, okay, in terms of safety, flexibility, and also versatility. Okay, and this benefit make them well suited for a lot of applications in batteries, fuel cell, electrochromic devices, and flexible electronics. Okay, so we go to the safety. Okay, for safety we have non-leakage. Okay, because polymer electrolytes are solid or gel-like. Okay, it will minimize the risk of leakage and improve safety in devices like battery. Okay, it also non-flammability. Okay, it is for safety. Okay, unlike liquid organic electrolytes, polymer electrolytes are less likely to catch fire. Okay, and it is make them a safer option for high energy application. Okay. Another one is the polymer electrolyte. Okay, withstand higher temperature without degradation. Okay, so it is beneficial for devices operating under demanding condition. Okay, because it is very good in terms of stability. Okay, now we get to the second part, okay, which is the flexibility and mechanical strength. Okay, the polymer electrolytes, okay, can be easily formed into thin films, okay, and it will make them ideal for flexible or wearable devices. And the polymer electrolytes also have good mechanical properties, okay, and they can be engineered to provide structural stability in devices, okay, eliminating the need for heavy, okay, rigid casings and reducing overall weight. Okay. For versatility, okay, the polymer electrolytes, okay, have a compatibility with various device shapes and design. Okay, the adaptable nature of polymer electrolytes allows for their integration into the devices, okay, with different shapes, okay, including thin film and flexible formats. Okay, and also it will it will have wide application range, okay, which is polymer electrolytes are used in diverse applications, okay, including batteries, okay, supercapacitors, fuel cell, and also electrochemical windows. Okay, and for the fourth one, okay, it will reduce dendrite growth in batteries. Okay, so as we all know, okay, in lithium-based batteries, polymer electrolytes can inhibit the formation of lithium dendrites, okay, which is the needle-like structure that can cause the short circuit in the liquid electrolytes. Okay, we call it dendrite. Okay, okay, and this improve the safety and lifespan of lithium batteries, and making polymer electrolytes a valuable component for next generation energy storage. And polymer electrolytes can improve interface with electrodes. Okay, polymer electrolytes, okay, can form better and more stable interface with the electrode materials. Okay, particularly in solid state batteries. Okay, and it will reduce the interfacial resistance. Okay, and another one is the electrochemical stability. Okay, many polymer electrolyte exhibit wide electrochemical stability windows and allow them to operate at higher voltage. Okay, this makes them compatible with high energy density materials. Okay, and it is beneficial in application like lithium-ion batteries and supercapacitors. Okay, second last one is the environmentally friendly potential. Is some polymer electrolytes, especially those based on biodegradable polymers or renewable resources, have less environmental impact compared to conventional liquid electrolytes. Okay, so gel polymer electrolytes, okay, can reduce the use of volatile organic solvent and making them safer for both users and the environment. Okay, the last one is polymer electrolytes can enhance design freedom for device manufacturers. Okay, with polymer electrolytes, manufacturers can produce thinner, more compact devices without compromising safety or functionality, and their inherent flexibility and structural stability allow for innovative device design, such as foldable batteries or integrated power source in smart textiles. Okay, so this is the application of polymer electrolytes. Okay, we can use in the lithium batteries, electrochemical sensors, okay, electrochromic devices, and fuel cell. Okay, for today's, I want to show you my research, okay, in use of polymer electrolytes in the electrochromic windows, okay, in the electrochromic devices. Okay, what is electrochromic devices? Electrochromic devices are materials or systems that change color or opacity in response to an electric voltage, okay, and it is allow them to adjust light transmission or reflectivity. And all of this, okay, commonly used in application like smart windows, okay, displays, rear view mirrors, and even an eyewear. Okay, so we can say that electrochromic device, okay, work based on electrochromism, okay, which is the phenomenon where the materials undergoes a reversible change in color or transparency when they gain or lose electron. Okay, you can see this is the example for the electrochromic windows. Okay, it will change its opacity. Okay, it it can also change the color. Okay, from transparent to blue. Okay, and come back to transparent state. Okay, this is how the electrochromic windows work. Okay. Uh, there is this is the what do you call it diagram, okay, for the electrochromic device. Okay, this is the principle that we use in the electrochromic windows. Okay, in electrochromic windows we must have the electrochromic materials. Okay, we can use the metal oxide. Okay, which is we in the articles, okay, they always use the tungsten oxide, okay, because it is the most widely used for blue coloration, okay. So we can also use the polymers, okay, for the electrochromic materials. Okay, we can use the conductive polymers, okay, because it can offer the flexibility, tunable colors, and quick response time, okay. So we also must have the transparent conducting electrodes. Okay. We always use the indium tin oxide. Okay. Okay. Indium tin oxide is commonly used in the as a transparent conducting electrodes. Okay. But it is very expensive. Okay. So there is a lot of research. Okay, also use the fluorine doped tin oxide, which is a cost-effective alternative to ITO, indium tin oxide, with similar properties. Okay, and we also have to must have the electrolyte. Okay, either solid state electrolytes. Okay, which is the lithium-based and ion conducting polymers, or liquid electrolytes. Okay, which is lithium salt solution in organic solvent. Okay, as you can see here, this is the electrochromics diagram. Okay, they have the several layers of materials that we already talked about. Okay, basically, okay, in any electrochromic windows, okay, the central three layer here, okay, are sandwiched between two layers of a transparent conducting oxide. Okay, and to protect the 5 layers of materials, this one, they are further sandwiched between 2 layers of glass or plastic substrate. Okay, and all of the layers, of course, are transparent to visible light. Okay, as you can see here, this is the electrochromic windows in its lightened or bleached state. Okay, and this is the electrochromic windows in its darkened or colored state. Okay, and this darkening occurs from the edge, okay, then moving inwards, and it is a very slow process. Okay, okay, and it is range from many seconds to several minutes depending on the window size. Okay, this is my research. Okay, now I want to go to my research. Okay, So I prepare my polymer electrolyte by using the ENR50, which is epoxidized natural rubber 50. Okay, and why I use ENR50 as a polymer in this project? Okay, ENR50, okay, commonly used in a variety of application due to its enhanced properties compared to conventional natural rubber. Okay, because NR50 is a modified version of natural rubber where around 50% of the double bonds in the polymer change are epoxidized. Okay, that means oxygen atoms are introduced into the polymer backbone. And this modification provides several benefits, okay, particularly in terms of improve their chemical resistance, flexibility, and compatibility with other materials. Okay, okay. First step, okay, for prepare the ENR50 based polymer electrolyte. Okay, first step will involve the dissolution of polymer, okay, which is ENR50 in the volatile solvent. Okay, I use THF. Okay, the viscous solution of polymer electrolyte is obtained, okay, with efficient stirring using magnetic stirrer for 24 hours. Okay, and then the solution is cast, okay, cast in the Teflon mold. Okay, this one. Then after the efficient stirring, okay, for 24 hours, okay, the solution is cast in the Teflon mold and leave for evaporation process for 24 to 48 hours. Okay. And then the film, okay. Okay, this is the sample of film that we have. Okay, this is the ENR50 based polymer electrolyte. Okay, sample that we have. Okay, after we do the work. Okay, and the film then deposit after evaporation. Okay, and further dry in the vacuum oven, and then after that we characterize it. Okay, and all the experiment work is conducted in the glove box because the polymer electrolyte is very sensitive to the humidity and oxygen. Okay, okay, this one. Okay, after that we do some impedance plot. Okay, and this one we use the PC as the plasticizer. Okay, and then we have with high weight percent of PC of plasticizer, we shift the impedance to the lower value. Okay, then we want to do some electrochromic windows. So we have to make some electrochromic materials, okay, which is the TiO2 thin film. Okay, the titanium dioxide thin film was prepared from the tetraisopropyl orthotitanate solution and ethanol as a solvent by sol gel deep coating technique. Okay. Okay, this one is all of these are do on the ITO glass substrate. Okay, the film was deposited after calcination process at 500 degrees C for 1 hour. Okay, this figure show how the TiO2 thin film deposit on the conductive glass. Okay, and the conductive glass is deep between 3 or 5 times. And after first dipping, it is transferred for drying process in the oven for 1 hour. And then we proceed with further dipping and repeat similar step between 3 or 5 times. Okay. Okay, this is the actual dipping technique. Okay, you can see here, we will dip it, okay, in the salt gel. Okay, and this is the enclosed chamber. Okay, where we place the dipping equipment to prevent the impurities, okay, contamination of the CO2 film formations. Okay, this figure show the how we assemble, okay, and test the device with ITO glass, okay, TiO2 and NF50 based polymer electrolyte, okay, sandwich like structure. Okay, we make the device like a sandwich like structure, okay, which have the ITO glass, TiO2, and also NF50 based polymer electrolyte, okay, and then, okay, you can see here. This is a demonstration of an electrochromic device, okay, showing polymer electrolyte, okay, in the operating mode. You can see here, this is the transparent change to darker blue color, okay, from transparent to darker blue color, okay. Okay, the device is applied with a low voltage at 4.5 volt. And this process takes about 1 to 2 minutes to obtain a dark blue color. Okay. And then after we change, okay, it will become transparent again. Okay, so as a conclusion, okay, you can see from my research for electrochromic device application, okay, oxidized natural rubber-based electrolytes incorporating lithium imide, okay, because I use lithium imide, are potential polymer electrolytes, okay, and the majority of salt dual polymer electrolyte system have ionic conductivities about 10 to the power of -5 Siemens per cm, okay, and plasticizing epoxidized natural rubber with PC, okay, and lithium imide salt solution significantly increase their ionic conductivity. After we add the plasticizer, okay, we have the higher ionic conductivity for the polymer electrolytes. And the polymer electrolytes that applied in the electrochemical device, okay, we observe that NR50 based polymer electrolyte are able to display the blue coloration state efficiency in electrochromic device when device is applied with a low voltage at 4.5 volts. So that's all for my presentation today. Thank you.
Okay, thank you, Ibu Anis. And now we have the second speaker, Professor Gunawan. Prof. Gunawan, the time is yours, Prof. Gunawan. You have 35 minutes.
Okay, thank you, Mr. Basit. I would like to share the PowerPoint. Can my PowerPoint be seen? Hello, Pak Basit? Hello?
Yes, Prof. We can see it.
Okay, thank you.
Bisa,
Thank you.
Pak, bisa.
Okay. Okay, I would like to say thank you for Dr. Basit who have give chance to speak about my research. Maybe it is a little bit different with the previous discussion, but it is all about preparing the semiconductor for photoelectrochemical water splitting. Photoelectrochemical splitting. So the title is thin layer copper indium sulfide and modified CPCT indium sulfide as a photoelectrochemical water splitting synthesized from various sulfur source. Why there is here, I think. What's wrong with this? So here is the background. So let's see fossil. Fossil fuel sources are non-renewable and resources are dwindling. So we have here there are several other energy that we can harvest beside the fossil energy, just like the wind from offshore, yes, offshore wind, and so also green electricity produces hydrogen like this, and then also hydrogen-based carbon emission-free renewable fuels. Actually, this is very promising. So, photoelectrochemical innovation of water splitting to produce hydrogen gas with the solar lights like this. So we use the photocathode here, and then it will produce for this example is a photoanode, and then it will produce oxygen, and then the cathode will produce hydrogen by illumination with the sunlight or artificial sunlight here. And the potential of a copper indium sulfide semiconductor based photocathode or develop of synthesis methods and effort to improve the properties and performance. So actually the absorber is a copper indium sulfide, and then on the molybdenum glass covered with molybdenum, and then we put the copper indium sulfide as the semiconductor absorber of some copper indium sulfide. Then cover with type cadmium sulfide here, and then we use the flow catalyst here to improve the performance. In this case, we add with the PT platinum. And then next, development of synthesizes methods and efforts to improve properties and performance. Here we can see there are several types of photocathode that has been prepared for photoelectrochemical water splitting here. So usually copper indium sulfide is an inorganic semiconductor because it is very stable and the water. The copper indium sulfide, and then it is modified with the cadmium sulfide with the indium sulfide and S2, etc. Here you can see. This is a way to improve effort with the buffer layer and co-catalyst modification. This is to improve the performance of the photocathode actually. And then also how to synthesize the copper indium sulfide itself also very important. So copper indium sulfide can be synthesized by electrodeposition and sulfurization. And the other way, maybe we can use vapor deposition, vapor metal deposition, something like that, and also using spray pyrolysis, and also like the Dr. Clip method and something like. And then the different sulfurization result in different photochemical values. You can see here. Effect of sulfurization also influence the copper indium sulfide produced. So in this case, we have title thin layer copper indium sulfide, and notified with the PT indium sulfide as a photoelectrochemical water splitting synthesized from produced sulfur salts. So we use from this case the source of sulfur from thiourea, from H2S, hydrogen sulfide, and also using sulfur powder. So it is the introduction for photoelectrochemical water splitting. So photoelectrochemical water splitting is the process of splitting water into hydrogen and oxygen when irradiated with a sufficient light energy using semiconductor thin film as electrodes. So you can see, and this is the artificial lips, the example of the artificial lips. So the process is when there is a light, the electron will excite to the conduction band and leaving the hole, and the electron will reduce water, become H2, become hydrogen gas, and then the hole will oxidize the water, become oxygen, become oxygen, become oxygen. So I will point that. Here is the process of reduction of water, producing water, and then here is the producing of oxygen here from the process of water with hole that can produce oxygen. And then from the energy here, there is a different energy between O2 and H plus here. The difference is 1.23 electron volts. This is actually when you use to split water, theoretically we can use potential around 1.323 volt. But for the real, practically, it is more than that value. So when we see from the oxidation and reduction process here, I'm sorry, this is in Indonesia. This is oxidation. Actually, there is water oxidation, which will produce oxygen, and potential oxidation is around minus 1.23, and then the reduction for water will produce ethane. So the total reaction is usually occurs as hydrogen and oxygen with the potential around 1.23. And for the CO indium S2, how we call that as chalcopyrite material. Chalcopyrite materials with a direct band gap in the range of 1.3 until 1.5 electron volt. And it has the absorption coefficient about 10 or the 5 centimeter minus 1, visible as the photo-absorbing component in the solar energy conversion system. So here's the example of chalcopyrite by using a catalyst. Usually we use platinum for catalyst. So with the band gap 1.3 until 1.5, it will covered at the visible light. So we can harvest the sunrise from UV light and the visible light. So that is the outstanding of the copper indium sulfide. Actually, also we use thallium to dope the copper indium sulfide. So we call that as a copper indium thallium sulfide or selenide as the absorber here. So here is the role of co-catalyst. So catalyst, there is what is it, one picture here. So buffer layer is a layer placed between the copper indium sulfide, protoanode, and the electrolyte to improve surface reactivity and water splitting efficiency. Co-catalyst acts as a site for electrocatalytic reaction, help accelerate the reaction rate. So the the best co-catalyst is that there's the value delta G here around 0. So for platinum, rhodium is a better co-catalyst than the other like here, like for molybdenum, argentum, or chromium, copper, something like that. So here is the way how to make the more efficient for copper indium sulfide. Copper indium sulfide modifier layer and co-catalyst here for water splitting. And it is the way how to prepare. As I stated before, for preparation copper indium sulfide, just like my student now works also, we can prepare by using spray pyrolysis. Yeah. Copper indium sulfide, we can spray to molybdenum substrate as a glass substrate. Yeah. And then we can have copper indium sulfide, but also using cutter plate and another process. Yes. That is the. But for electrodeposition process is very simple, yeah. And also, as long as I know, the electrodeposition is a very good to produce copper indium sulfide with a good efficiency. Electrodeposition is the process of deposition or coating of material by electrolysis. So we use 3 electrodes here. Here is the prime electrode. Usually we use silver chloride electrode, and the working is the molybdenum glass that covered with molybdenum, and then we deposit one by one, copper first, and then indium, and then after that we do the sulfurization. So if there is a problem with deposition of copper, so we cannot continue with the indium deposition. And also, if there is a problem with indium deposition, we cannot continue by sulfurization. So that's all have a problem for that case. So the way how to deposit copper and indium in this case is very important to get good deposition. So we have to attenuate the potential in this case, so that we can have a copper and indium with the better thicker deposition. Sometimes after deposition copper, we cannot deposit indium. So that is very tricky for this case. And then sulfurization. After we deposit the copper on molybdenum and continue with the indium, so we can say that as a stack deposition here. So we do a sulfurization here, sulfurization. So molybdenum that covered with the copper and indium, we blew with the sulfur here, so that it becomes copper indium sulfide. In the glass tube, yeah, the glass tube furnace, glass tube furnace. We use the argon gas to blow the sulfur gas to react with the copper and indium. So we use the hot plate with the temperature, with the certain temperature here, we can set. The sulfurization method is a chemical process in which certain material and all substances are treated with sulfur salts to change their composition to sulfur containing compounds here. And here is the process. This is a procedure you can see here. So stack electrodeposition copper indium on molybdenum glass. So we use the molybdenum glass. For the good back contact, usually for P-type, we use molybdenum glass. So some research using FTO, but they have to cover with the silver or gold on the FTO just to make it have a good contact here. The coating was started from the copper and continued with indium successfully with three electrode reference electrode and counter electrode and working electrode here. So the dimension around 0.7 times 1.0 centimeter for the molybdenum that we use in this case. Yeah. So we do electrodeposition, then we got the copper indium, and then after that we do sulfurization using H2S, sulfur, urea, and then we will get the copper indium sulfide. And then after that we deposit the indium sulfide on the our previous works using cadmium sulfate also by using chemical bed deposition. So it will copper with indium sulfide. P-type copper indium sulfide will copper with N-type indium sulfide at the window. So after that, by photoelectrodeposition using platinum, we will cover the absorber with platinum, but it will not cover all the electrode because it will block the light if we cover it with the platinum. But this is that nanoparticle that the light still can go through to the absorber here. And then for the application of the photocathode, we use here also three electrodes here working. So we use the photocathode here, and then copper counter electrode using platinum and reference electrode. And then we give a light with artificial light 1.5 EM for the process of electrochemical water splitting. So for sulfurization, we use 10 minutes at 400 Celsius. After 3 minutes, the sulfurization variation of urea to sulfur H2S was flown with 200 milliliter per minute nitrogen gas posed in a glass tube furnace. So we use glass tube furnace. And then after that, by chemical bed deposition here, we can deposit the indium sulfide on the copper indium sulfide. And then surface modification with platinum. In this case, we can see here by using 1 millimolar H2 PtCl6 solution here. So this by illumination here for deposition of platinum with the potential around 0.1. Then we can continue. Result in discussion. So for the first time, A is the set of measurement here. Set of measurement. We use the potential stat here to measure the photocurrent, and then the set of photoelectrochemical water splitting like this. So we use sodium sulfate as the electrolyte, and then with the similar electrode, counter electrode, and reference electrode, and working electrodes. Working electrode is our photocathode, photocathode. And then for electrodeposition here, you can see the copper deposition in the P, and then also this one is indium deposition. So from this we can see synthesis and characterization of copper indium sulfide. Actually, after copper indium sulfide has been formed in this case, we have to wash with KCN, potassium cyanide, to remove copper sulfide, copper sulfide that still exists in the material. So that copper indium sulfide also, and there is a copper sulfide that it should be removed by KCN, potassium cyanide. So after that, we will have copper indium sulfide, and then we characterize using XRD, SM, ATX, Raman, XPS, UV phase DRS, and photoelectrochemical test. So after characterization, we do through phase modification here. And then we also do SEM, ATX, XPS, and photoelectrochemical potential type. And then for photoelectrochemical test and HC gas evolution, we do in the third steps here. So we can see here, here is the electrodeposition of indium for this case here. Then electrodeposition of copper, and then we continue electrodeposition of indium. So we can see there is a red, red color of little bit white here of copper here. So sometimes if we get a very red color, indium will not deposit here. So that is very tricky to deposit indium on the copper actually. And then after that we do sulfurization using SOS, sulfur, and urea. So here is the way how to the instrument for deposition of sulfur on copper indium. So then we can continue. So here is the reaction actually. Maybe we can let's say. And from the characterization, we use here some ATX here, and here for the surface analysis using SEM, SEM, and then this is the cross section of the SEM, copper indium sulfide. So you can see that the result is the porous here, porous copper indium sulfide. And also we can see the ATX. Here we can see the S. Actually, the best way to get the copper indium sulfide should be copper 25, indium 35, and S almost 50 here. But for this case, this is around 48 and 45, 40. Yeah. So this is almost 112 here. We never find the precise value for copper indium sulfide, as my previous work also result like this. We can see here the microstructure and then the relevant mechanism of the copper indium sulfide here. So as I said before, besides the copper indium sulfide, also form copper sulfide, copper X sulfide, that it should be removed from the copper indium sulfide so that it will not influence the performance of the copper indium sulfide. So we remove it by KCN, potassium cyanide, yeah, to remove the copper sulfide here. And from the XRT here, we can see the chalcopyrite, the structure of the copper indium sulfide here, the characteristic chalcopyrite structure. As evident by the 2 theta diffraction pit at 27.87 here, 27 here, beautiful. And then 46.37, this one, and 55.01, 55.01, this one. And indexes as a plan like this, and of the, this is as indication of a copper indium sulfide chalcopyrite. So we index it using CCTDS database number 320339 particularly. And the diffraction pattern of copper indium sulfide would write lattice parameter located at 2 theta 26 here. Wood side here, wood side here. 20, 26, yeah, 27, 29, 47, and etc. So for copper indium sulfide deposited by using sulfur here, there is a different character. So yes, it has a character of wood side. Meanwhile, for copper indium sulfide from H2S and urea, it will have chalcopyrite type here, chalcopyrite type. And then for the XPS, we can see here for the 3 copper indium sulfide prepared by H2S, sulfur, and urea here. So there is a different here. So this is for copper. And then for indium and N2S to peak area at this one here can be observed. So there is a different character of copper indium sulfide prepared by H2S, sulfur, and urea from the XPS actually. And then by Raman, you can see the dominant feature of Raman plot is intense peak and 298 here. This is as indication of copper indium sulfide, chalcopyrite, originating from vibration of sulfur superlates here. So actually from the 3 copper indium sulfide prepared by different sources, prepared by sulfur sources as almost copper indium sulfide characteristic by Raman. So from DRSUP here, so actually DRSUP is used for determine the pen cap of the absorber, in this case copper indium sulfide. So we use CIS means copper indium sulfide. So after we convert the absorbance to South plot here, so we can find the band gap around 1.52, 1.81, and 1.74. That is for CIS prepared from H2S to current theory respectively in this case. So actually with the different sulfur sources as the different band gap in this case. And for photocurrent result, photocurrent test. So in this case, when the light is on, and in this case is when the light off. So if the material has no semiconductor characteristic, we will not or not have a characteristic like this. For P-type, always it will have the profile like this. So for N-type, the curve will be on the upside, But if the P-type, the curve will be downside. So in this case, we use when the light on like this, and then when the light off here, then the light on, return back here, and then for several seconds, we turn off the light and then return back to this. So why we do this? We just want to know whether when we have no light, it should be zero. Should be zero. Should be zero. When we have light, it should have current here. So if we have this case, it means that our material has the properties of a semiconductor. So if it has no current like this for the P-type, so the spectrum, the characteristic is not up here in this case. Although we have measured band gap and etc., but if there is no current, actually it is not usable in this case. So from this case, we can see that the copper indium sulfide prepared by H2S, sulfurized by H2S with higher photocurrent here compared with sulfur and urea. So this one is 2 milliamp, so we can count the few, maybe around 10 or maybe 12, yeah. Our previous copper indium sulfide also until 18 milliamp per square, centimeter square. So, and for the photoelectrochemical water splitting liquid bias, actually for the P-type and N-type should have meet each other actually in this case, so that we don't need the bias, I mean, without the electricity from outside, I mean, without applied potential in this case. So by combining the N-type and P-type in this case, photocathode and photoanode, so we can produce hydrogen simultaneously with producing electricity from outside without applied potential in this case. So for what is it? For ideal, yeah, for ideal it should be have a structure like this. Yeah. Photoanode with more positive and photoanode with more negative here, so that there is a what is it in operating current here. This is operating current today. So the high operating current will produce the higher oxygen, high nitrogen here. So here is the formula for measuring the solar to hydrogen efficiency. So by using two electrodes, photocathode and photoanode, we can measure the efficiency like this. And then after that, we can see modification of with the indium sulfide here. So we use water pads here to deposit the indium sulfide. This is around 70 degrees Celsius to deposit indium sulfide. And then copper indium sulfide, we immerse here to the indium sulfide so that it will cover with indium sulfide. but this is around 1 hour. I forget this. Yeah. So it will cover indium sulfide. So we call this as a chemical bed deposition. And then after that, we deposit nanoparticle of platinum by using 0.1 sodium sulfate uh, with illumination by illumination, so that nanoparticle of Pt will deposit on the indium sulfide, and then we can check by SEM the possibility of indium and platinum, whether it is deposited or not from the SEM ATX also. So we can see there is platinum in indium, and this one is copper indium sulfide. Actually, around not more than 1 micro for copper indium sulfide. I don't know why.
Apologize, Prof. Gunawan, you still have around 2 minutes.
Okay, I will continue. Make it fast, yeah. Okay. And this is the photocurrent for the platinum indium sulfide covered with the indium sulfide covered with copper indium sulfide covered with indium sulfide and platinum. So you can see here the SOS also still has a higher photocurrent, I see, and also surface modification also here. The effect of surface modification also increase the onset potential in this picture. And then, so for measuring the efficiency, we use APP, applied by potential. You can see here the black one is for copper indium sulfide prepared by sulfurization using HOS. It has a higher efficiency in this case. And then also I will continue this. Here is the scheme for preparing for deposition of for preparing for its oxygen generation is equal. And then by using PC, we can measure the oxygen and hydrogen release, and we can have a curve like this. Okay, I think it's enough for this bit. Maybe it's too long for discussion. And also, if you have more discussion, maybe you can read the journal. Okay, thank you very much, Pak Basit, Mr. Basit.
Okay, thank you, Prof. Gunawan, for the very nice presentation. Now we are at the Q&A session. For any participant who want to ask your question, you can write down on the chat column, or you can just raise your hand to give a question to our speakers. To let you know that Chemist Anis has left the seminar because she got a fever. That's why she apologized for not joining us after the session. Okay, so anyone, you can ask question to Professor Gunawan.
Online.
While waiting for the other participant, Prof. Gunawan, I just want to ask. So you use electrodeposition and sulfurization in what's the name? Sequential process, right?
Yeah.
And then how does this kind of process can enhance the structural and also the optical properties of copper indium sulfide, Prof. Gunawan?
Can enhance.
Yeah. So it's like the performance of the device is really based on the quality of
Yeah.
the layers, right? And then you do the
Yeah.
sequential electrodeposition here.
Actually, before I have done the co-deposition, like indium, copper and indium, we join together, and then it doesn't work here. Also, the current is not so high. So the best way for me up until now might be by stack deposition for copper and indium, and then continue by sulfurization. And also there were other methods like copper indium sulfide we make first and then we deposit on the molybdenum. And also it has a low current, low photocurrent, because maybe there is an organic in the in the copper indium sulfide that cause that that hindrance the maybe the current, on the copper indium sulfide and the molybdenum. I don't know. So we have to remove the organic that can be used to deposit copper indium sulfide and on the molybdenum like that. Maybe the best one is by vapor deposition, by using uh, what is it like vacuum, vacuum deposition of metal, copper and indium, and then continue with sulfur. That is maybe the answer. Is that can be if that can answer your question.
Yes, I think it can answer. So I would like to invite the other participants to give a question to Professor Gunawan.
I want to ask one question, Pak Basi.
Okay, go on to Yayu.
Yeah, okay. Thank you, Prof. Gunawan, for your presentation. You do a lot of research, related to the electrodeposition. Electrodeposition and also water splitting, So you presented about the making multi-layer of gold Cu, indium, and also sulfur. And in the last, you modify the film with the platinum. You know that platinum also can be used as a catalyst. So, and then in this photocathode is based on like photocatalytic properties, is it right or not, Pak Gun? Because you need how to say, you need UV, you need a light in order to activate the photocathode. So if I don't know whether you can, how to say, like can change a platinum with the other, and then what actually do with the platinum, because platinum can be used as a catalyst, not for photo. I mean, it can be a platinum can work even though there is no light or UV light or any other lights. Maybe you can just explain. I don't. Maybe I need to. Okay, because this is out of my expertise. Okay, thank you, Prof. Gun.
Okay. Actually, if we use absorber, like copper indium sulfide or like silicon, actually, if we illuminate the semiconductor, it will produce electron and hole, the electron and hole pairs, Then an electron will goes to the surface, and when it will go to the what is it, in the system of the uh, photoelectrochemical water splitting, or to the like a solar cell, to the applied to the instrument outside, like a fan or something like that, or LED, like anything there, something. And then if we don't use catalyst, electron will tend to to go back to the valence band, or we can say that as a recombination. So for electron that will not will that if the electron will not if you don't use a platinum, electron will return back to the conduction band, so valence band. So it will make a recombination. So there is no flow of electron on the outside flow, yeah, outside flow on the surface. So we use catalyst here just to hold the electron will not return back. Yeah, so that is the way. Yeah, also actually it's also similar like the catalyst and the catalyst as usual. Yeah, hydrogen also platinum also as the absorbent uh, that will use for water to react and that the platinum and will after that if there is an electron it will reduce the water become on hydrogen. But if there is no platinum, the electron will tend to return back to the valence band. So that is the way how to do in the water electrochemical water splitting. But if we use like europium as the electron scavenging, yeah, electron scavenging, electron will be attracted by europium so that it will not return back uh, to the valence band. So by adding the platinum as a catalyst, it will also enhance the photocurrent. So the prediction can be the recombination of hole and electron pairs. Maybe like that message.
Okay, thank you, Prof. So meaning that we can also use another
Yeah.
kind of catalyst, yeah.
Yeah, my previous work is using rhodium. Yeah, rhodium.
Or
Also, you can use like iron oxide. Maybe we can try to do that. Okay.
yeah. Thank you, bro.
Okay.
Okay, thank you, Bu Yayu. I think time is up now. It's already 3 p.m. of Indonesia time. So once more, thank you very much for our two speakers here, Chemist Anis, who already left because of she's not at a good condition, and for our second presenter, Prof. Gunawan. So let's give a big applause for both of our speakers. Okay, thank you for both speaker, for all of the audience, for both University Diponegoro and Universitas Malaysia. Don't forget, we still have the sixth ya Bu Ayu ya.
Yeah, the last one in this.
Yeah, the last one, the sixth join webinar series on chemistry. So stay tuned at our webinar series. We'll see you again on the sixth webinar series and a good or better condition. Apologize for any mistaken during this process. We'll see you later. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.